Okay, I guess we can start because it's 4:15. I hope more people join. So my name is Marko Vukolic. I'm one of the original Fabric architects, and I lead basically consensus development in research and development in IBM Research Zurich. So this is our latest work that's going to be finally Fabric ordering service, but not only that, it's meant to be a standalone library that other blockchains can integrate with. So I was hoping actually for more audience given the topic. But so as you will see, Mir-BFT has quite unique features. It's the best throughput on wide area networks BFT consensus protocol to date, and maybe in foreseeable future for the features that you will see. So just about consensus in blockchain a bit. So when I say consensus in this talk, this is going to be basically the mechanism to replicate this blockchain if we see it as a totally ordered list of transactions, like grouped into the blocks. Blocks are totally ordered across nodes, and within a block we have essentially a list of transactions. So that establishes the global total order. So the network is untrusted. We are going to focus on permissioned blockchains, but whatever I'm going to say is basically applicable to proof-of-stake permissionless blockchains as well. So consensus protocols are those protocols that keep the blockchain data structure like identical across the nodes. So in Fabric speak, this is the main job of the ordering service. And consensus for blockchains has an interesting history. Like the problem on its own, like predates Bitcoin. So consensus in untrusted networks is a problem that was introduced in the 80s. But of course, the popularity gets with Bitcoin. And we know the major drawbacks of Bitcoin's proof of work, right? So it has high energy consumption because it's based on essentially very lightweight mechanisms. So miners independently mine blocks, which can lead to forks. This basically gives us probabilistic finality. So without going into details, combined with essentially openness of the network, that Bitcoin is a permissionless network, and this high energy consumption, we have essentially as results low throughput up to 7 transactions per second, right? Depending on how you configure the block size and the block frequency. In Bitcoin, it's maximum 7 transactions per second and very high latency. So 10 minutes for 1 block confirmation, 1 hour for 6 block confirmations. Which is why essentially all blockchain projects go to replacing proof of work, right? Virtually all, not all. And the main idea there is to rely on Byzantine fault-tolerant consensus to circumvent proof of work issues, right? And then you have a bunch of protocols that are employed in different blockchains. And this is basically the area where we have the bridging of the gap between permissionless and permissioned blockchains, right? So Tendermint or Cosmos would use a Tendermint BFT, which is exactly the same BFT that you could use in permissioned blockchains, right? If you weight votes basically by stake. Okay. So this work in one slide is a robust. I'm going to talk more about what I mean by robust. But it's a robust BFT total order consensus protocol with highest throughput on wide area networks. We measured up to 100 because this is like the setting which is the most relevant for permissioned blockchains. You will rarely see any use case where, for example, the number of orders in Fabric network or total number of peers even would go over 100, but like it's probably more because you will see how plots scale. And it's suitable for permission and proof-of-stake permissionless blockchains. So just a bit of formalism. So this gives the model. I'm not going to bother you too much with the model, but this gives basically the model that we are working on. If you have questions about membership reconfiguration, we can postpone them to the end of the talk because I'm going to assume a fixed membership of orders for simplicity. Like n of them, and up to 1/3 of them can be malicious. Any number of clients can be malicious. So this is a pretty standard model. Then the different protocols differ in synchrony assumptions on the network. So you have protocols like Algorand, which would assume more synchrony than I'm assuming here. You have protocols like Honey-Badger, which assume less synchrony than I'm assuming here. But this is the model assumed, for example, by Tendermint consensus and PBFT consensus, which is eventually synchronous network, which means that up to certain time called global stabilization time here, I give an acronym GST, the network can be completely asynchronous. This time is unknown to nodes. So basically, the protocol needs to tolerate arbitrarily long periods of asynchrony. But it's only required to progress once the network is synchronous, which essentially means that the safety properties that I'm just going to list need to be maintained even if the network is purely asynchronous. And liveness or progress on the network is guaranteed when the network is synchronous. So eventually. These properties are summarized as follows. So for total load of broadcast, we have agreement. So essentially, roughly speaking, right? So all correct nodes deliver transactions in the same order. Validity, they only deliver transactions proposed by some clients, so you will not get your garbage on your blockchain, right? So there will not be the ability of malicious nodes to produce something that just appears on the blockchain. No duplications, transactions are not duplicated. There are different mechanisms how this can be solved. And liveness, so these are all, essentially the first three properties would be safety properties. They are guaranteed even if the network is completely asynchronous. And liveness, which says that every transaction proposed by a correct client is eventually delivered by all correct nodes, is a liveness property and is guaranteed with synchrony. Any questions? Because we are a small crowd. Any questions regarding the model so you don't lose me now? Okay. So before I give you a protocol that aims to be highly scalable and to have extremely high throughput, let's understand in classical leader-based protocols such as PBFT, such as Tendermint, what are the bottlenecks. So for example, we have here I'm working with 4 nodes, out of which one can be Byzantine. I'm not going to even spare this Byzantine fault, but this is just how the protocol works. So there are 2 approaches. I will first stick with one, when the request dissemination is tied with the ordering protocol itself, which means in this case that the primary assembles the set of transactions. Here I have 4 transactions in a block or in a batch, and it disseminates the whole block, including the transaction payload, to all the other nodes. Then there are 2 all-to-all communication steps, at least in PBFT, in which basically nodes talk to each other, saying, well, leader told me that this block should be added to the blockchain. What did he tell you, right? Because the leader can be Byzantine, malicious. And essentially, we need this all-to-all communication, which can be circumvented. Some consensus protocols, such as hot stuff, they really aim at reducing the n-square number of communication steps. But as we will see, this is not very, very important. For some reason, they need to do it again. Like, I will need half an hour to explain you why. But with 3 f+1 nodes, they cannot really stop after one step of all communication. They need to do it once more, but not more than that. You can actually skip the 3rd step if you have 5 f+1 nodes, but that's a separate story. So now if 2/3 majority, if qualified majority agrees on the same block, then basically correct nodes can add this block to the blockchain. So what's a bottleneck here? As n grows. So now we want scalability, n grows. Here I have n equals 4. N grows. Which step of the protocol is the bottleneck? Any idea? Commit. Let's assume there is no execution. So let's think fabric, so we just add the block to the blockchain. So there's like not much work there. It's up to the peers to execute or not. We don't care too much. Let's focus on the ordering service. So it seems like a classical answer would be the mid 2 steps, because they have n-square communication. But one thing that I want you to notice is this is load balanced across n replicas. So these 2 steps, the work, like the load on a bottleneck replica, is actually O(n). It has nothing to do with O(n)². And then it pushes us back to the 1st step, especially if you disseminate the requests along with the block. So the bottleneck in classically is the 1st step. Especially if you disseminate transactions with the block, basically the agreement there goes on the hash of the block. So you're like these 2 n-square communication steps are really, really lightweight. And the bottleneck is in the 1st. So as n grows, essentially you have the limited bandwidth at the primary, at the leader. It needs to disseminate, it needs to replicate this basically n times. So there are optimizations to this that I will come back to, in which you include only hashes of the transactions in the block. But as you'll see, this creates problems. Let's assume for the moment that basically we disseminate the payload inside the main ordering protocol. So as the number of replicas grow, this is a simple basically plot, the size of this message grows linearly, and of course your throughput, which is illustrated on the right-hand side, goes inversely proportionally to the number of nodes. And this is the pattern that you see all over again in leader-based protocols. Actually, this is the reason and not the n-square number of messages. So approaches such as hot stuff, which limit the number of messages in the common case to ON, have nothing to do with scalability. So what's robust BFT? Robust BFT that Mir, so it's a family of protocol that Mir belongs to, which basically began with aardvark hardening. Aardvark is the protocol essentially by Clement and others in NSDI 2009, which is basically hardening of PBFT to give you guaranteed performance even in the presence of attacks. So in blockchain, of course, we can hope that there are no attacks on the network, but like it's better that we design the protocol. For example, now in Fabric, we have been waiting for a few years for a protocol. We are not going to redesign it once people say, but there actually are active attacks on the network. So if it's BFT, then it's BFT, right? So it should perform well even under attacks so long as the network is synchronous. So this is the main path that Mir is following, right? So which is to avoid pitfalls of fragile optimization, such as relying on clients to disseminate requests. Because there are many protocols, like PBFT, if you read the TOX 2002 version, so the journal version, or hot stuff, for example, hot stuff is specified such that the leader disseminates the payload inside the block, but it's implemented such that the leader disseminates the hash of the payload inside the block. Which is okay, of course, intuitively, because you can rely on the client to disseminate the payload to the replicas. And because you now load balance across clients, each client submits its own transaction, this should be okay. Like from software implementation perspective, as n grows, requiring the client to send, for example, to 100 ordering service nodes each and every time it's a Visa transaction, it's a separate problem. But let's assume we allow it, right? And then the Byzantine client comes and says, well, look, I don't have an incentive to do this, I will just send it to the leader. And it's the main issue, right? So you have the client is not following the protocol, it's submitting a transaction to the leader, to the primary. This looks exactly the same like this case. There is no way leader distinguishes at this moment. It proposes a pre-prepared message, it proposes the block, and the others don't have the transaction. So at best, if client disappears, they can go to the leader, or if they want to kick out the client, they need now to agree that the client should be kicked out, so this is an incomplete protocol. So the easiest fix to this is basically that nodes require the primary to give them finally this payload. And we don't want this, like we want a simple protocol than this, and more robust. So how Mir-BFT evolved? So I'm going to give you on this slide, basically the idea how it works. But essentially there is another, there is a throughput bottleneck on, as we scale the number of nodes, as we grow the number of nodes, the leader needs to disseminate the whole block to all of them. This we mentioned. There is another one. Unless you have several blocks in flight, then the latency of this 3-message delay pattern basically blocks you how many blocks can you have in flight, right? So if you wait for one block agreement to finish before you issue another block, then basically your latency, depending on the block size, impacts the throughput. Which is why many protocols, including hot stuff and BFT Smart, have this notion of pipeline PBFT, where to circumvent that other bottleneck, the leader is allowed to propose blocks in, like, if it proposes block number 1 without waiting to finish agreement on this one, it proposes block number 2. So this is called pipelining. So it's a nice trick that we are going to use, but on its own, it doesn't solve us the problem. So I'm referring to the topmost picture. It doesn't solve us the problem of the leader bottleneck. For fairness, like this was introduced by spinning in literature and Tendermint in blockchain practice, there is this rotation of the leader after every block, which is nice for fairness. If you want to give rewards to the block producers, this is nice, but basically it doesn't solve any of our problems. So in spinning and Tendermint, you have this latency that dictates how many blocks can you have in flight. For example, if this 3-message delay is half a second, you can have 2 blocks per second throughput, and then depends how many transactions you can stuff in a block. But it's a nice idea that we will be using. It would be just nicer that we use this bandwidth that first and the second leader have roughly the same time. So this is the main idea, which led us to our interim design. So Mir doesn't look like this, but at some point 2 years ago, it looked like the third picture, where we essentially wait just from the next leader to get the block, which is prioritized from the first leader, and then it disseminates. So basically, we cut this time short between the blocks, and we try to use the bandwidth in a more efficient way. But then we realized, of course, there is a better way to do this, which is to do this. And this is essentially how Mir-BFT works. It's like imagine multiplexing several BFT instances together. So you first shard, in modular arithmetics, you shard the block number space, and each leader is responsible for a certain, for certain modulus. For example, first node proposes blocks 1, 5, 9, and 13, those that give basically a modulus 1 with division of number of leaders, and so on. And I'm showing here just the prepare messages. So there are several instances of the protocol, and those, it wouldn't be visible, nothing would be visible on the picture if we would be showing all these n square messages, right? But they are there. They are sent all the time. So this is the main idea. And it's not rocket science, so the question is, why wasn't this proposed before? And there is a main issue, which is called request duplication. So I'm coming back to that, but here I'm overviewing main principles on which Mir-BFT is built. So I would like you to focus first on the third bullet, which is incrementally built on PBFT. So this three-phase pattern that I showed is repeated all over again. All over again. It's just that we have now the first bullet, multiple leaders, and essentially we are multiplexing. It's a single total order. There is no sharding, right? But we use the sharding ideas to essentially divide the leadership of the blocks, right, across the leaders, and then we are multiplexing this in a single total order. We need to do it in a way, and this is the key novelty of Mir-BFT, in a way to prevent request duplication, and I'm coming back to this problem in the next slide. And we have several optimizations to boost the throughput even further. One is called light total order broadcast that I'm going to spend some time on, which is doing this dissemination of hashes by the leader properly. And you will see what I mean by properly. Also signature verification sharding, and I will mention something about our highly parallelized networking and implementation. And there are some tricks we are using there to boost the throughput when the number of nodes is small. Okay, so request duplication, this is the main challenge. Of course, you can do this multiplexing, and the thing that can happen is the following. So there, I'm again back to 4 nodes. Client sends the same transactions to 2 nodes. And of course, if they start their PBFT instances independently of each other, what can happen is they just add this transaction to block number 1 and block number 2 in parallel. They propose it, and basically at the end of the story, what we get is we order blocks 1 and 2, fine, but there is this great transaction in both blocks. So if the client does this to all of the nodes, so it sends it n times now, basically if my transaction appears n times, I really didn't improve the throughput, right? If you think about the terms of good put. Yes, my transaction, I have very many transactions flying on, but one is repeated n times. And your good put is basically going to scale 1 over n, just like it did with leaders. So you cannot do this, right? And this is the main challenge. So there are certain proposals that go into this direction, but they don't solve this problem. So these, I'm not going to name protocols, but these solutions assume that client will behave nicely and send the transaction to 1 node. What can happen then? We can have the leader not behaving nicely and dropping this transaction to the floor. So what can client do? It can go to the second order and submit the transaction there, and voila, there you have the problem again. So it's not easy to blame the client if the transactions appear more than once. It's actually impossible. And even if you put, because in Fabric we work, for Fabric ordering service, we work without currency, right, without cryptocurrency. Even adding payment for transactions here doesn't solve the problem. We can discuss it in Q&A session if you want. So how do we solve this? Well, we are going to use sharding of transactions by their hash. So again, there is no rocket science, but there is a nice combination of all these concepts into a single protocol. So essentially, we're going to partition the hash space of the transactions into so-called buckets. In this example, I will have as many buckets as the leader. Normally, we have many more buckets than the leader, so we can kind of load balance better. But with 4 leaders, it's actually very nice to divide the hash space in 4 buckets for the purpose of the example. And each leader has a different active bucket, which means that essentially, the leader 1 to propose blocks 1, 5, 9, etc., can only put their transactions from the 1/4 of the hash space, and so on for other leaders. As we will see, this is not sufficient because of this. If I'm always the leader for the first quarter of the hash space, I can always not liking basically Dave's transactions when he sends me, I can just drop them to the floor. So we need to rotate this assignment of buckets. So this is the main novelty in Mir-BFT as a protocol. So graphically, there below you have your hash space for transactions. And there I have 4 nodes. With full line, I'm denoting essentially I'm denoting the active bucket. So this node 0, proposes only from the blue bucket. And node number 1 proposes only from the red bucket, node number 2 from the gray, and node number 3 from this turquoise bucket. And this basically corresponds to the quarter of the hash space in this example. So there is a transaction coming in. It hashes to the blue part of the hash space. This is a collision-free cryptographic hash function. There are no cheats. So basically SHA-256 in our implementation. It hashes to the blue portion, and now basically it means that it can be only proposed by the node number 0. There is another transaction coming. It hashes to the gray part of the hash space and belongs to this node. And basically for a certain time, which we call an epoch, only those nodes are allowed to propose these transactions. And then at the end of the epoch, we are essentially rotating the assignment of the buckets. Which means, for example, now the node number 13 is faulty, or we reach the end of the epoch. We are just rotating the assignment in a way that now the node number 3 is responsible for this bucket. So it's going to propose, provided that it has the transaction, right? So in limit, we still require the client, as any BFT protocol must do, to submit, in the worst case, to F+1 nodes. Because whenever it submits to F or less, you have this strange attack of censorship where F malicious nodes just drop the transaction to the floor. So you cannot guarantee liveness. And this is an easy proof that any protocol needs to do it. And there we go. So the number of nodes, I will show you some plots in which the number of leaders is 100. And you can say this is very optimistic. So what we do is when the faults happen, we shrink we shrink the leader set. Basically, we still have, at this stage, we have the primary, which is round robin like in PBFT, and primary decides what is his leader set. It's like you have the prime minister and decides his government. Basically, there are certain rules in which if we had faults happening, the leader set must shrink. And if faults didn't happen, the leader set must grow, or should grow, right? Because it can stay the same. To avoid the churn between, like, if some process is really faulty, to include it back again in the leader set and exclude it, you don't want to do this all the time. So the details are in the paper, but this is not the most trickiest part. So here I'm giving you the policy. We are growing and shrinking leader set by 1 leader, but this is really what we are going to make this is a tunable part of the protocol. You could be aggressive, you could cut the leader size in half, you can grow it faster than +1, so there is basically the tunability to the protocol. The main principle is if we detected that basically we didn't make progress with that number of leaders, we are going to grow the leader set. And if we basically made progress, we are going to, so if we made progress, we're going to grow the leader set. If there are faults, we're going to shrink the leader set. So then we have, this is vanilla Mir, how it works, and we have 2 optimizations. One is when the network is basically the bottleneck. And it's, if you want, it's disseminating the hashes in a proper way. So what this means in a proper way, basically we are going to deliver the transaction as opposed to delivering the payload of the transaction to every correct node. We are going to deliver the hash of the transaction to every correct node, and we are going to deliver the payload to at least 1 correct node. which is interesting for Fabric because, as you know, in Fabric, the peers pool transactions from certain orders. So strictly speaking, you don't have to guarantee that all orders have all the transactions. You just need to make sure that the peer can find these transactions in all places. So how this works is basically that f+1 of the nodes get the full payload, which is disseminated by the leader, and others can get the hash, like the block with hashes, so-called the light block or the light batch. And then the agreement basically proceeds as normal. It's just that you kind of sharded this payload to f+1 nodes. So the peer is guaranteed to find it. Of course, this will be tunable, and you can switch it off. If you don't like it, it's too complex, you want your ordering service nodes to all have the payload, just switch it off. I will show the impact on the throughput. Signature verification sharding, this is for client authentication. Each, of course, I didn't show this so far, but each client transaction is signed by the client signature. And essentially what we have in the protocol so far is, I didn't show these signatures, right? So they're verified by each and every node in the system. Of course, you can apply the similar principle as for light total order broadcast that I showed, and basically have only f+1 nodes validate this signature. So it gives you constant increase in throughput when basically you have a very fast network and the protocol is computationally bound by signature verification. But like it gives you basically 3x throughput on paper, which basically translates in our experiments to 2x or something. So these are two optimizations that we use in the protocol. So this is the most interesting part, which is the performance evaluation. So for details we can discuss, or I can point you to the paper. But basically then we compared Mir to several baselines. One is the chain replication. So this is not really used. So it's really the best performing total order broadcast protocol for clusters. It's not very popular for blockchains because how it replicates is very optimistically. So it's like if we would enumerate all of us in the room and do the replication by just me sending the message, the block there, and then the block gets replicated in a chain pattern. So it's fragile to false because if you have any node failing, basically we have the chain cut, but it's really nice as a baseline. Because apart from latency, it's really throughput efficient. And I'm going to use it just for the baseline to show how actually Mir performs. Then we compared to Libra hot stuff to our version of PBFT. So the single, we basically specialized our code to do a PBFT single leader version of it. So we can compare to single leader protocols. And we did this on local area network, which is less, although most of the deployments currently are on a single cloud, we are focusing on wide area networks. So we went to 100 nodes, up to 100 data centers on IBM cloud. These are the specs. And when we got the VM, we got the 1 gigabit full duplex bandwidth. We tested with 2 transaction sizes. One is like what most of blockchains have, and one is what this very popular blockchain has, because it carries the X509 certificates. But we wanted a useful number for Fabric, right? So I would like to see this disappear and actually go here, but this is a totally separate discussion. But like we tested with these 2 transaction sizes. Okay, so on wide area networks, the performance looks like this. So this is Mir, this is chain, this is PBFT. And this is your any, if you will, this is your almost approximating your any leader-based protocol. The absolute numbers are like, you see this bump in scalability just because, for example, if you do, so this is both optimizations. So this is with signature verification optimization. For Bitcoin size is actually only signature verification optimization. For 4 nodes, you have half of your, like f+1 is 2. It's not 1/3. You have half of the nodes verifying the signature. Whereas for 16 nodes, this is actually 1/3. So there is this bump in throughput, which is actually better than if you go with 4 nodes. But then it stays flat, and it's going to drop like when network becomes the bottleneck. So here we are compute bound, and the bound is actually the signature. How many signatures can you verify with this, with basically these specs per second? And the protocol here doesn't even matter, so it's flat, which should be ideal scalability. Chain scales ideally, but then it's on the lower, like much lower, and it has issues with latency, right, as we'll see, and this is your leader-based protocol. Absolute numbers are like 60,000 transactions per second So these are Bitcoin sized. It's just nothing to do with Bitcoin here, but we are validating every client signature. So there is no cheating here, right? So this is almost all the work that you would do in a Bitcoin application. This is hot stuff. So that's hot stuff, and that's Mir. Okay? Now, hot stuff is the version that sends hashes only. So we just took the code. Hot stuff sends hashes only, although the protocol specification says that the leader should send the payload. So it relies, what I showed, it relies on the client to disseminate the request. And it doesn't have client authentication. So basically, nobody checks these client signatures. So I'm really not advocating this. I'm definitely not advocating this, but then we tune Mir to do exactly the same to have apples-to-apples comparison. Mir performs better with 4 nodes, and this is because of our trick. We actually open, when we have few nodes in the ordering service, like few orders, we open many TLS connections among them, not just one. So if you read the geo-replicated papers, they would typically give you the bandwidth between the two sites. But do you really believe that between Brazil, Amazon Web Services, or IBM data center, and that in Europe you have 50 megabit throughput? You don't. But this is the limit on a single connection. Just go and open another one. And this is basically the effect. So we open several connections in parallel, which basically go around the bandwidth delay product limitations of the TCP, and basically you get better throughput. Now, hot stuff doesn't do it, and as you grow the number of nodes, now the leader can disseminate the request to actually more and more nodes because of this effect, right? But it stops at some point. At some point, which is actually with 60 nodes, you reach, even if the leader disseminates just the hashes, you saturate the network. And from then on, it just behaves how it should be, which is inversely proportional to number of nodes, whereas Mir scales much better. The absolute numbers are higher, but this is because we are now not, again, we are not verifying validating client signatures, so absolute numbers should be taken here as a grain of salt. These are not the numbers that should be expected from actual robust implementation. But it just shows the scalability trends. So again, it's not important how many messages your consensus sends, like ON versus ON square, but basically there is this idea of multiple leaders and request duplication elimination that makes sense. Of course, you can make a Mir version with hot stuff if you're happy. We are just not doing that at the moment. This is Fabric. The red line is Fabric validation bottleneck. Why, if somebody asked me, pick a protocol and implement it, put it in Fabric, I was saying we actually need something else. It's hopefully obvious from this picture. There is nothing to pick. Because as soon as you cross 10 nodes, anything that you pick is a bottleneck. And since we are not going to do this n times, this is why we took time and actually went and designed. So this is Mir performance. I'm not happy with this either. I would like to see this flat. But this is mostly because we attribute this to heterogeneity of nodes, at least on IBM Cloud. So that 1 gigabit, if you take Brazil data center, is not really transforming to 1 gigabit, even with multiple connections, etc. But basically, we have a certain drop. Basically, what this plot shows is that for any deployment of Fabric, up to 100 nodes, the BFT ordering service is not going to be the bottleneck, which was the main inspiration for this work. So this was achieved. Now, impact of optimizations, okay, you told us about this LTO and signature verification, but these are really tricks. I don't want to use them. If you don't want to use them, this is the Bitcoin size. So now this is the snapshot for 16 nodes, any 16, across 16 data centers on IBM Cloud. This is vanilla Mir, and this is the 60,000 transactions per second I reported. So if you don't like the optimizations, you're going to end up with this, which is pretty impressive still, right? So you're going to lose some 30% of the performance, but you will still be at 40,000 transactions per second. This is the impact of rotation, right? So bucket rotation, we need it for basically to eliminate censoring by Byzantine replicas, and it turns out that there is not much impact, right? So there is a 10% impact. You need to do it. It seems expensive, but it's not. So this is what this point shows us. Here, I'm just focusing on latency. Here, again, I have 16 nodes, 16 data centers. This is now Fabric size payload. Here we got the numbers for throughput, right? For when we get the throughput to the saturation. So we are increasing the number of clients until basically throughput grows. As we increase the number of clients, the load increases and the latency, basically there is queuing in the system, latency grows up. This is why it shoots here. So latency you can read here. Typical latencies you read here, right? When the system is not under saturation. And these are basically about 1 second. So you can expect that on wide area network, for example, in deployment with 16 nodes of future fabric ordering service, you get 1 second latency of the ordering service. This is the duplication prevention impact, but I would rather, do we have time? Like, what is the time? Okay, there is still some time. Actually, I have 5 minutes, right? So I would like actually to have questions. But this is the impact of duplication prevention. So this is if we like eliminate the duplication prevention and I let, like other protocols, I let Mir propose without this sharding of requests, right? I let them propose anything, I let the leaders propose anything that they get. And basically, if the client sends to f+1, this is the blue plot, and if the client sends to 3f+1, there is a lot more duplicates, so there is the purple plot. And essentially, because this is measuring good put, because the transaction is duplicated f+1 or 3f+1 times, the good put is actually much lower. This is the performance with faults. You can observe some, like if we have 16 leaders and we actually crash the leader, the protocol reconfigures and goes back to 15 leaders. So you do kind of have the throughput dropping to 0, but basically then you have the shoot up and then you're delivering in a burst, right? So this should be actually, I should put on this plot the average throughput, which would go like something like this. And then you have the example where 2 leaders fail, and then we go back to 14 leaders, and then we include the 15th leaders, etc. But basically, you see that the average throughput is not, in this example, would be probably around 30,000 transactions per second or so. So the protocol does actually eliminate leaders and come back to the good performance. So we stressed it a bit. There are more stressful experiments in the paper, so I invite you to read it. It's currently fighting its way through basically to get published. There is a lot of competition, like a lot of people seem not to be liking this idea, but they will eventually go through. The main news is basically this. So it's going to, now we are discussing how, like which features, I would like that all features that I discussed here with you are present in the production implementation of Mir-BFT that's going to be integrated with Fabric. I had a timeline here, but I removed it. I don't want to overcommit, but I hope that we get something this year, right? Definitely at latest early next year, but like this is, if you ask, this is opinion of me as Marko Vukolic, not commitment really there, because we know it's an open source project, there are many variables there.
So is it implemented or is it going to be?
It's implemented, but there is the implementation, which is kind of IBM proprietary, which I would like to get open source, and like I hope, regardless of it's just for the repeatability of the paper, it's going to probably be that. But then we are essentially, we started re-implementation based on this code of what's going to become an open source implementation. Yeah, so it's it's finished and it's ongoing at the same time.
So will it be part of Fabric as a pluggable?
It's yes, as a pluggable thing, but as an independent library. So much like Raft is completely independent, and then we is the same concept. Which is also nice for other blockchains, I would say, if you want to use it. So I will stop here. I have actually many different experiments, but they don't give us too much of a new insight. Like, actually, we did really, really thorough experiments. They are all listed in the paper, but I would rather actually take a few more questions in this 2-3 minutes that we have left. Yes?
Do you have an assumption that none of those is stable all the time, or you assume that some dynamic number of those, and how do you approach it?
Yes. So this is a good question. The question is, do I assume a static number of nodes or dynamic number of nodes? This is so the change in membership is the problem that any BFT protocol needs to solve. So we take on it really orthogonally here. So there will be a membership. This is one of the reasons we are doing now the production implementation with membership reconfiguration, because it was not present in our let's call it proof of concept, right? This one that was really stressed. And the version so we couldn't have a version integrated in Fabric which doesn't have this feature. So we're going to have it. More questions? Yes.
Is there any restriction about the type of the transaction? So if we assume that with one type of the service payment, that could be easier, but in typical public transaction required to record about the state to some of the state transactions. So I might say the sharding might be affected such a stable transaction.
So here I took the problem apart, much like Fabric does, in a sense that the execution, of course, like all these numbers, if you're going to execute, if your treatment of transactions, here we are just ordering. And validation is already doing something in Fabric. So if you put an application, these numbers are going to most probably drop down, but this is our goal precisely. So we don't want ordering service to become a bottleneck. That's our job.
You mean the data will be done into the starting order already, and the beginning of the before the submitting to the next buckets.
I'm not sure I'm following, really. Maybe yes. Yes, one question here.
So suppose I'm willing to set F to be much lower than normal, say like the root F. Are there any easy optimizations that would dramatically increase?
Quite a lot. Quite a lot. From the pattern which if root of F is I said with F5, F+1, we are not even talking about three-phase protocol. We are talking about two-phase protocol all the time, actually, probably correct. And there are other optimizations. Now you can start gossiping the payload much easier. Because here, the gossip really, we talked about client dissemination and leader dissemination. You have something in between, which is gossip. And gossip, essentially, if you have F, as soon as your fan out is lower than F, this is attackable, right? Which, if your threshold is root of N, then you're much easier. It's much easier to do a fault-tolerant gossip. But there are a lot of simplifications in this case. Yes.
What performance do you expect from that?
Honestly, so I didn't give you with 1 gigabit, this point is 500, 600 megabits per second. So this is so what I expect is better latency, to a certain extent better throughput, but not much, but it doesn't really even matter at this moment. So at this moment, I would say we need to implement this library properly. It needs to be robust. It cannot be just reporting the best case numbers. And then we are back to the main story of this forum, which are applications. But at least we get this problem over. For permission blockchains. I'm arguing that this has huge impact on permissionless, but of course, let's take this for some other talk. OK, thanks a lot for your attention. Thank you.